you find the answer of that book. And I'll come and talk. No, it's not talk. You go read it and you answer it. No, really, which one? If those things you didn't study, that's your fault. I'm going to let you do that, you know, because you didn't study what you're supposed to study, you know. But out of the question, how do you grade it? You know, you said difficult. You know, for example, problem. For example, problem 2 is a transform, right? Just I'm making it as simple as possible. I'm saying forget XM, forget artsy, forget the laws, and basically it's going to be R and X. It cannot be simpler than that one, right?
Yeah.
So do you think that one is difficult?
No.
Okay. So that's it. How about the history system in the current law?
No.
Okay. So, and how about the three-phase system? Compared to what you have in homework.
Oh, yeah.
This is much easier, right? Just I want to let you know, if you study your homework and your notes, usually you are good if you study. But if you don't study it like that, somebody was asking me what's the vector group. Even he didn't know what's the vector group, you know. I said, okay, if you have, see, this is when I was somewhere for interview, they ask me a question. For example, they're telling me, hey, can you tell us how this inverter works? Yes, I know that. I start to talk about it. But they'll ask me, how do you know PN junction? I don't know this kind of MOSFET works. I'm not going to even think about it because I don't know. I don't have any clue about it. You know what I'm saying? So I said, no, I don't know. But if you let me know, give me time. I'll go study for the interview. Now, if you are in the exam. The exam is different from interview. You cannot go read it and come back. You know what I'm saying? You have to answer it there. If you haven't here, for example, the word vector group or phasor group or I don't know, those kinds of things. So you should blame it all on yourself. Just put it this way. Now I'm saying, because this is what you are supposed to do. We spend like I don't know, half an hour, 1 hour to go through this thing to explain it. And it's a very simple thing. It's a phasor diagram. When you draw this, vectors for the voltages and those kind of things, and you get the phase difference between the call it clock, see what time is simple like that. Now, going back to the exam, I think lots of you guys didn't do very well. I'll put it this way: you were not familiar with the style of exam. I'll put it this way more than to say you guys didn't study enough. I think part of it was you didn't study enough. But I'm not going to consider that one. I'm saying you are not familiar with the style of exam. My style of grading is I'm not going to curve it. Just make it clear. And I'm not going to make curve it. Whatever you're getting, you're getting. But there's a good part about it. I'm not going to fail everybody. Don't worry about that part. I would like to keep my average class usually between B minus, B and B plus. Maybe the class size is a little bit bigger, maybe B or B minus, but I like to keep it on that range, For those when they didn't have a good exam, don't worry about the exam. Just when we give you the grade, see where you are. If you're on the average of the class, for example, let's say the average is 60, for example. If you are around 60, you are safe. Grade 1 to get a pass. Grade, you're not going to get an A. If you get 60, for example, in your midterm, so A is gone. A minus is gone, probably, but if you are around the average, so average of my class usually is around B, unless everybody wants to fail, so I cannot do anything about that. For example, we go to the final again, you guys do a study at all, I'm not going to give you the free gift, to be honest, I'll try to push it that way, but if at some point I see, okay, this guy looks like they don't deserve it, forget it, let's go ahead, just fix it, But those when they have had class with me, they know my style. Usually I keep my grade, around average around B. That's what I like to have, for class, especially in type of class like this. But it depends to you guys. You should study. You should study those kind of things. How many times did I say in this class, when we have a 3-phase system and they give you voltage is 100, what does it mean now? How many times did I say that? How many times did I say that? Still, this is a kind of really bad. It's still, some people they ask me, is this 208 phase voltage? I'm not going to answer those questions, like it or not. Because it means you didn't listen. This is not once. things, I'm not gonna answer those kind of. And it very pisses me off, I try to not get pissed off, but when I say something, I said something 100 times, again you go ask the same thing, I'm thinking, me kind of pissed off, well, we didn't even listen once in this class, what we're talking about. And one more thing, I cannot be here for December, I think it's the 5th, the last day of the class. I think it's the 5th or 4th, something like that. That's the last Thursday of the class. I cannot be here. I have to go to Michigan. And I'm going to have a makeup class, not this Saturday, next Saturday. We're going to be here maybe for 2.5 hours, because we have Thanksgiving also, and so, as I said, not this Saturday, but the Saturday after, I will tell you what kind of, I'll watch college football. I'm not college football. I'm waiting to see what time the Ice State Michigan game. Here, Michigan is hopefully it's like late afternoon, so we can come here 10 o'clock to 12 finish, and you guys do. But if the game is noontime over there, so we're going to come but probably 3:30 or like something like that. So we're going to have a makeup class next Saturday, not this one, next Saturday. I'll set the time, what time is it exactly. And I think we shouldn't have any problem with the classroom and this kind of thing. There'll be in Warren or somewhere over there, we will find a place to do for that.
Can we expect the grading on the exams to be similar to the grading on homework?
No. Because she grades the homework, I grade the exam.
Okay.
But usually I'm very generous.
Okay, so it's not like, it's not right or wrong.
Usually grading homework, I think they are a little bit easier on you guys, when they're grading homework. But I'll try. You can ask those when they have other course with me. There are like at least 10 of them here. You can ask them, what did you expect? For example, guy sitting in front of you, he has a course with me. You can ask him, to say, what did you expect? What did you do? I think I have seen this is in my reviews. I read the reviews to get it right. Most of you said, okay, I got better than what I thought. This is what you guys say. And my task here is not to scare you. That's not what I'm doing here. The exam, believe me, I try to make it as simple as possible. Because my intention here is to get your interest. I want to make you kind of fall in love with the power system, power electronics, those kind of things. I want when you are leaving this course, you say, oh, that was a great course, Hopefully you can say that at the end, I want to go to this field. That's my intention of teaching this course, Not, to kind of fail you, no, that's not my intention, When I was younger, it was like, I started to teach when I was, maybe 6 months of my class failed that time, But it's going to have better and better and better and better, much better now, maybe 5%, 10%, as I said, that's the ratio. But my intention is to make you guys interested in this field. Hopefully you get enough out of this field to say, oh, this is maybe a good area to continue to focus on. And we'll try to grade the exam as soon as possible. I'm really bad in grading. I'm very lazy in the grading. But try to do that as soon as possible to give you the grade. The sooner the better. And we're going to have 3 more homeworks, or maybe 2. I may combine the number 2 and number 5 and 6 together, give you the homeworks a little bit earlier, but it's okay, so problem number 1 to 4 for the homework number 5, and I don't know, 5 to 9 for problem homework number 2. I may do that because the time is very limited. We have to cover it.
For ECE188 next quarter, is it safe Tuesday, Thursday, 5 p.m.?
Is what?
Is the class going to be Tuesday, Thursday, 5 p.m.?
Not for
For ECE188 next quarter, the energy conversion, is the class time going to be like Tuesday, Thursday, 5 p.m.?
Yeah. All my classes, is Tuesday, Thursday, 5 to 6:30.
Because they've not opened up. Because they've not opened up seats, so there's no like enrollment for this class.
We limited to 48 students, for the problem we have is the lab, This course has 4 labs. So basically we could swap, you say, you would, we started from like 3, 5, 7, 9, and we had, I think, 4, 6, 8, and 10. That's the way it goes. But over there, we have 6 experimental labs. You cannot do that. We don't have that in the budget to do that. And that's the same setup you are using right now. So we could have a maximum, I think we could have a 12 per session, so 12 times 4 is going to be 48. The maximum we can do, you guys can judge it. If we put 4 people on those tables, it's okay. Right now you are 3, as we did that. Do you think 4 is okay?
Yeah.
Okay? I think the less, the better for you guys. You learn more. I think 4 is 4 is okay? I think yes. To me, honestly, I think it's too much, But if we see suddenly there is a wait list, I don't know, 50 people over there, we may do that. Maybe 4 students per table. So that one is going to open up. From 12, it's going to go to 16. 16 times 4 is going to be 64, But really, the other problem we have, we don't have any trained people to be in the lab. Arno is the only one right now. Hopefully, you guys will pick up. Next year, we will not have this problem. Instead of 4 sessions for the lab, we put 8 sessions, so we can cover, I don't know, we can cover 90 people, in the lab. But right now, we don't have trained people to teach the lab. That's we have to stick with Arno, and Arno can teach only 4 labs, not more. That's the problem. That's the limitation of the university. We can teach only 4 labs. Any question?
So is Arno going to be the 125A TA? Or
No, Arno used to be by 125. We've been teaching those for the past 3 years, but he will be fully, used for the 121. The professor is looking for a TA for that, and Arno is not doing 125. It's going to be 121. Any other questions? But for those when they want to stay in the field of power, I recommend you to take those courses. They take most courses, they are pretty good courses. Okay, so we finished the inductance calculation for different ones with a single phase system, 3-phase system, with the bundle conductors and all those kinds of immediate transposition and all those kinds of. We finished the inductance calculation. Now we're going to move on to the capacitance calculation. And some people they said before we here, this phasor diagram, this phasor group, vector group is not in the book. I checked the book. Check the page 118, 119, and 120 of the book. It's explaining exactly what it is in phasor group. Check those things. I thought initially it's not in the book, but it's there. Look at it, you will see that. And the other problem with this course is this is the first time. There is no sample. Usually if you go to power electronics 1, I'll give you 4 different samples of each exam, midterm and final. I don't give the samples for myself, but for this course we don't have any sample questions preview before exam, and usually you have to wait until the evaluation exam. Anything you want to talk about it? So we are going to go to capacitance calculation. Capacitance calculation. So before we move to the transmission line, single phase and 3-phase system, let's see how we can calculate the capacitance for a system. So just I'm going to put it here and I'll roll it right over there. We say Q is equal to CV, right? That's the rule for a capacitor. You know this from the physics, right? So basically C is equal to Q over V, right? If I have 2 plates, 2 wires, 2 conductor, whatever, I have 2 of them. If I want to calculate the capacitance of the two, I need to know how much Q I have, I need to know how much V I have, I can divide it by each other and find the C in capacitance value. But to calculate the voltage, from, for example, point 1 to point 2, let's say we call it V12. Usually we need the, usually we need the E, D, E is the electric field. For example, let's say we have a Q coulomb here and minus Q coulomb here. So we have this electric field here. So basically we need to calculate that E, how much is the E, and after that we calculate the voltage. Voltage between these 2 points is EDX from here going to this point. So when I to calculate V, I need to calculate E, right? And to calculate E is the electrical field. We have a magnetic field, which is flux and V and those kind of things, and we have electrical field. To calculate the electrical field, again, you have it from the, I'm not sure which course. Usually we had this one in the, physics, because when I was a bachelor student, we had physics, mechanics, physics, thermodynamics and physics, electricity physics. We had this in electricity, part. I'm not sure what's the system here, but there's a Gauss law, right? You use the Gauss law. You said in this is the Gauss law. You have a closed surface. To calculate the E on that surface, use this rule. And Q net is the electrical charge inside that closed surface. So basically, to calculate the capacitance, we have to go through this three. One, we need to calculate the electrical field. Which is the Gauss law. So basically, EDF, there's an epsilon here also. Or Q divided by epsilon. EDS, Q net, or Q enclosed, or epsilon. That's the Gauss law. Can you see it, Daniel? This markers, they're not that good, So we have a Gauss law. We calculate the electrical field, and after that, we need to calculate the voltage. Yes.
Is that Q net over C?
Yes. No. Epsilon. Epsilon. And next is the voltage. Let's say voltage calculation. We say V between point 1 and point 2 is EDX. We calculate the E here, and after that we calculate the voltage, and at the end the capacitance. So we use this equation. We say C is equal to Q over. So basically we need to go through this step to calculate the capacitance. Now let's start with this one first, with the E calculation for this system, for a simple system, how we can calculate it. Let's assume we have a conductor here. Let's say we have a conductor like this, and we do this one for the unit of the length, which is in the metric system is a meter. So there is a charge, electrical charge here. Let's consider this one, for example, is the Q coulomb of the electrical charge is here, and is uniformly distributed on this wire or conductor or whatever it is. So we want to calculate the electrical field in the distance length is 1 meter. We are doing it for 1 meter, right? And this is the center of the cylinder, right? And the electrical field is going to be like this. It's leaving this point. This is the positive charge. Electrical field is leaving this one. And let's say this distance is, for example, R. I don't know what we call it here. For example, is X. This distance is X. And here on this circle, everywhere, the electrical field is constant and is E. We call it E on this circle. Here is E, E, E. Everywhere is E. But if I go a little bit further, the value is going to change. We're going to calculate how much is that E, in that cylinder. Now we'll go use this one first. So electrical field is radial, right? So this is the E dot ds. There are two surfaces. One surface is here, right? And there's one surface here and one surface here, right? If you look at if we have a surface, the ds, the vector of the surface, how we define the vector of surface? If this is surface, this is the ds. This is the direction of ds. This is the vector of the surface, right? Normal to the surface. So basically, for this one, look at here, for this area, the normal to the surface is this way, right? E is radial, and this one is this way, right? How much is the angle between the ds and the E? 90 degrees, right? So basically, this is the dot. Cosine of 90 is going to be how much? 0, right? The same thing for the surface here, right? On this side. Again, the ds is that way, the E is this way, so 90 degrees. So basically, on this surface and this surface, there is no, the EDS is going to be 0, right? Now, let's go for this one. Let's go for this. E is radial, right? For example, at this point. How is the normal to the surface? Is radial here, right? So basically, ds is going to be like this. So basically, E and ds, the angle between E and ds, this is like a vector, because I'm talking about the vector of this angle. So angle between E and ds is how much? Is 0, right? So basically, E dot ds is going to be E ds, right? Now, one more thing before we go. If you have a circle, right, and the radius of this circle is r, and if this one is a theta, how much is this length? Theta is a radian, the unit of radius. How much is this length? R theta, right? This is r theta, right? Just I'm reminding you of a little bit things from geometry and calculus and those kind of things. Now, consider here. There is a small angle here. We'll start from here. And this angle is d theta. How much is this length? How much is this length? It is going to be this length. How much is this one? This is x d theta, right? I have this little one here. So basically, EDS is going to be, on this surface E is constant, it's going to come out from this integral E. So this one is going to be integral of ds, it's going to be here, see? This one is the ds, right? How much is the ds now? This length is 1 meter, right? This length is how much? X d theta, right? Basically, 1 times x d theta. Basically, it's x d theta, right? This is this ds, right? This radius is x. This angle is d theta, right? This length is going to be x d theta. Now, this is my ds. the value of ds, not the normal. You know what I'm saying? We have a normal of ds and we have the value of ds. How much is the ds? Is going to be length 1 meter times this length is x d theta, right? So basically here, ds I'm going to replace it like this. X d theta, and the theta is going to go from 0 to how much? 2 pi, right? So it's going to go from 0 to pi. Basically it's going to be 2 pi x e. So equal to how much? I forgot. How much electrical charge we have inside this cylinder? How much electrical charge we have inside the cylinder? Q, right? So this is equal to Q. So basically E is going to be Q. I missed one thing. So Q over epsilon. Yeah, epsilon. So it's going to be Q over 2 pi epsilon x. So the unit is volt per meter. That's the unit of the electrical. So if we have a conductor, now we know how to calculate the electrical field with in a distance of x or whatever from that electrical conductor, right? So now I know this one. Let's go back here. Again, I have the same conductor, and there is a Q-coulomb bar here, right? Now I want to see how much is the voltage difference between these 2 points. For example, I have 1 point here. Let's call it P1, for example, and this one P2. This is the P1 and P2. I want to see how much is the V12. I want to see how much is the V12, right? So this one is in the distance of, for example, let's put it this way. This one is in distance of, for example, V1 from here. This one should be center. No. This is D1. And this one is in distance of D2 from the center. So we have 2 points. One is a D1 far from the conductor. The other one is D2 far from the conductor. I want to know if I have a Q-coulomb, electrical charge here. What is the voltage difference between these 2 points? Let's assume one of them is positive, one of them is negative. I'm going to mark this one positive voltage, this one negative voltage. So I want to calculate the V12, basically is VP1 minus VP2, which is VP1 minus VP2. So to calculate this one, I'm going to go use this equation. So I'll say this one is equal to E dx from where to where? From D1 to D2, right? How much is E? I calculated here, right? So it's going to be basically the voltage difference is going to be Q over 2 pi epsilon ln of top one minus the bottom one is going to be D1 over D, D2 over D. This is the voltage difference. calculate the voltage. Here we cannot calculate the capacitance because we have to have for calculating capacitance, we have to have a two conductor or two surface. There is a Q here, for example, minus Q here, and now there is an electrical field between these two, right? Right now, the second conductor is in infinity, you know what I'm saying? This one, the electrical field from here is coming and going to the infinity, you know? But in real system, for example, when we have a capacitor, we have a positive plate and we have a negative plate, right? And we want to calculate the electrical field and the voltage and the capacitance between two surfaces, right? Now, before going there, I want to give a general equation. Here we have only one, right? If I had, I don't know, 10 of them, I have 10 conductors. They have one is a Q1, one is a Q2, one is a Q3, all of them. Now if I wanted to calculate the voltage difference here, how is it going to work out? Like exactly what we did. We did this for 1 year, right? And keep in mind, see, just look at this too. Is a Q over 2 pi epsilon ln of d2 over d1. d1 is the positive one, right? Just keep in mind. d1 here is the positive one, right? In the denominator. And the d2 is the negative one, right? Just keeping this one in mind. Now let's say if we have, I don't know, m conductors, for example, right? Each one has some electrical charge. Let's calculate the we have, for example, 1, 2, I don't know, go up to, for example, this is number I, this is the number K, and this is the number M, small m, and we have a total of M conduct. This one has a Q1, Q2, this one has a Q1 charge, this one has a Q2, this one has a QI, and this one has a QK, I don't know, QM, and QM cap. So we have an M conductor. Each one they have this much of, electrical charge. Now we want to know how much is this voltage. Let's say plus, minus. I want to know how much is this voltage. VKI. I want to know how much is the VKI. Let's start from here. We said we have this one. So basically, we should go one by one, right? I should start from here. This one. How much voltage I'm going to have here? How much? See, I want to see how much voltage I have here, how much voltage I have here. And there is only one conductor. This is a superposition rule, right? Let's assume the rest, they are not here. Forget everybody. Only we have one, right? I want to know how much is the voltage difference between these two, right? Basically, based on this equation, it said Q1, because we are looking at the conductor number 1, right? It's going to be Q1, right? Times 2 pi divided by 2 pi epsilon ln of the negative should be in the denominator and the positive should be in the denominator, right? So basically, how much is the distance of Q1 to K? Let's call it, I don't know, we call it L, something like that, D1K, right? We are going to have a D1K here, and we're going to have D1I here, right? D1I here, right? So basically, this is the negative. It's going to be D1I divided by D1K, right? If you use this equation. So now let's go for conductor number 2. We calculated the voltage difference because of Q1, right? But there's a Q2, right? Let's calculate the voltage difference for the Q2, Q3, Q5, all of them. Add them all together, it's going to give you the voltage difference for all the loads. So basically, for charge for QM, if we consider only QM, right? Let's say this is this distance is D, I call it MI or IM, I'm not sure what we call it. We call it DIM, and this one is DKM, right? I have a charge here, QM. I want to calculate the voltage difference between these 2 points because of this charge, right? Based on that equation, it's going to be, we call it what? We call it VKIM means voltage difference between Ki and I because of M, because of the charging point M. So it's going to be equal to basically Qm over 2 pi epsilon. Ln of what? Can you tell me ln of what? Ln of what? Look at here. It is going to be negative, right? Look at here. This is the negative one, right? D2 over the positive one, right? So it's going to be Ln of the negative one, this one, is the negative side. DIN over the positive one, DKN. Right? So we calculated, this is the same equation I have here, but just I made it a little bit more generalized, using this K, I, M, and those kinds of things. I calculated the voltage difference between point I and point K because of the charge M, right? How many of those charges I have? I have M capital of them, right? Let's say M capital is 10. I have 10 charges, right? So if I want to calculate the total voltage, so how much is the VKI? Basically, the sigma VKIN, M from 1 to M, right? Put the M1 is going to give you the voltage difference because of the charge number 1. Put 2 is going to give the voltage difference because of charge number 2, right? And you can go all the way. So basically, VKI is going to be 1 over 2 pi epsilon sigma MF from 1 to M Qm ln of DIM over DKN. Ln of DIM over DKN. So M is going to be 1, 2, 3, 4, 5 until M cap. So I calculated the voltage between these 2 points because of generated because of M different charges, right? Now we use this equation as a base and we can calculate any capacitance we want in this system. We'll start from this one. So this equation is the base. Basically it started from here. And that one is just adding these things together, for 10, 20, whatever number of charges you have. Now let's start with a 2-wire system. We want to calculate the capacitance between 2 wires. So we have 2 wires, and we want to calculate the capacitance between these 2 wires. For example, I have a wire 1 here. This one has a Q charges. Let's call this one wire X. And we have this one, wire B, has a charge of minus Q, wire Y. We want to see how much is this is what exactly you have, for example, every wire you have. Every, for example, single phase system, you have 2 wires. Usually the number is very, very, very small for the 2-wire system. We ignore that. But for the transmission line, the number is going to be bigger, and we have to calculate those kind of things. But let's see how much is going to be the capacitance between these 2. And let's assume this distance, let's call it dxy. X x from y, right? Now, if I want to calculate this capacitance first, I can say the capacitance is Q over Vx squared, right? This is like a simple capacitor. You say that I have a Q minus Q. If I know how much is the voltage, I can calculate the capacitance. I said capacitance is Q over V, right? So now I need to calculate the Vxy between these two, right? This is the positive and this is the negative. How much is the Vxy? Let's go with that equation here. So it's going to be 1 over 2 pi epsilon times. So the difference voltage between this point and this point could be because of this charge, right? That's one. Or could be because of this charge, right? So there are two. Basically, in that equation, m is 2, right? And I is going to be either x or it's going to be y, right? So let's write it down. It's going to be, so let me put it here. It's going to be q, let's say for this one, I'll put it qx. Qx times ln. I'm calculating the voltage difference between these two, right? Because of this charge. I call it Qx, but Qx is Q. Later on, I'm going to replace it with Q. The voltage difference between these two, because of this charge, is going to be ln of what? We said the negative, this is the negative, is going to be in the denominator, and the positive is going to be in the denominator, right? So basically, it's going to be dxy, right? dxy, and we call that one dxx. dxx basically is this. This is this R. Because we start from this point, right, outside of the conductor to the other conductor, to the outside of the other conductor. But we assume dxy is much bigger than R. If you are going to put it very, very accurate, you should say dxy, if dxy is from here to here. Let's say dxy is from here to here. If you wanted to put it really accurate, right, because you're going to calculate the voltage difference between this surface and this surface, right? You should put it dxy minus rx minus ry, right? But usually this distance is much, much bigger than the rx and ry. So basically we ignore that one. We say dxy minus rx minus ry is almost dxy. Right? But the exact number is this one. Because you should go from this surface to this surface. Usually dxy is very, very bigger than this and this. So basically we say this is almost equal to dxy. So we said that the voltage difference because of charge x is going to be this distance divided by this distance, right? Now the second plus I have a QV, Q1, ln of, tell me what? How much is it? It's going to be again the positive in the denominator and the negative on the denominator, right? This is the negative, right? So it's going to be what? dyy over dx, right? This is the voltage. And we know Qx is Q and Qy is minus Q, right? And let's put it this way. Let's continue, and after that I'm going to simplify. So Vxy is going to be 1 over Q over 2 pi epsilon ln of dxy over dxs xx plus minus ln of dyy over dxy, right? So basically Vxy is going to be Q over 2 pi epsilon. So this one is going to be ln of this divided by this is going to be dxy over dxx dyy, right? This is the voltage. How much is the capacitance between x and y? The capacitance CXY, we said it over, is going to be Q over VXY, right? Q divided by this, Q is going to cancel out, right? It's going to be 1 over, actually it's going to be 2 pi epsilon, if I'm correct, right? Ln of dxy to the power of 2 over dxx dy, right? That's the capacitance between conductor X and conductor Y. But now there is more assumption, more things here. Usually, not usually, dxx is equal to dyy and is equal to what? R, right? That's the radius of the wire. And let's call dxy, let's call it d, the distance between the two wires, right? The distance between the two wires, we call it d. The radius of each one is r. So basically, cxy is going to be 2 pi epsilon over ln of, this one is going to be d squared over r. And 2 is going to come here, so basically it's going to be pi epsilon over ln of d over r. Farad per meter. Remember, we calculated everything for 1 meter, right? This is the farad per meter. So these two conductors, they have this much capacitance between them, right? Now you can just imagine, just go think about it, epsilon, I think it was 8.85 times 10 to the power of, I don't know, minus something, minus 8, 9, 10, 12, something like that, right? So just keep in mind, this is a very, very, very small number, right? And if you have two conductors, just think about this one. This R is much, much, much smaller than this one, right? This is a big number. You divide it into a very small number by a big number, it's going to be a very, very small number, right? My point is that you have two wires next to each other, almost zero. The capacitance is almost zero. We don't consider that one. There are some capacitance, but you say it's almost zero. We ignore that. But you can calculate the capacitance value.
Over there, is that Qx is equal to Qy, which is Qy is equal to minus Q?
Yeah, Qx is equal to minus Qy. So because that again is simple. If you consider two wire, one current is going this way, one current is going this way. How much is the definition of Q? Q is the integral of I dt, right? How much current is passing during the time, right? Or other way, I is equal to integral of Q dt. I'm not sure which way is it. But so when current is one going this way, one is going that way, and the current is equal but negative of each other, so the Q's has to be equal but negative, right? So we calculated the conductance for these two, but usually, for example, in USA, not in the other countries. In other countries, usually they have a 220 volt or something like that for single phase system. But what we have here, we have a center tap. I'm not sure how you hear about this one. We have a plus minus 120 in US, So if you look at your home, usually it's like this. This one comes to your home, 120 or 110, I believe, or minus 120 and 0. This is what you have coming to your home. If you look at your stove, those one you use, they did a lot of, electricity for it. Because, the stoves, usually they have a very high power, they do lots of power to dissipate. So if they go with 120 volt, so the power is how much? Let's say the power factor is 1. Power is VI, right? If an I is going to be P over 1, V, right? If consider this one, if this one 120 or 240, If it's a 240, the current is going to be half, right? So basically, for the big load, they use a higher voltage. But for the rest of the home, like refrigerator, I don't know, like the lights, you know, whatever else you have in home, they use the 120 volts. The only one usually is the higher power in regular home. You know, if it's I don't know, laundry house, they have a huge, you know, laundry machine. That one again needs the 240. But the one we have at home is 120 volts. You know, usually you use the one line and one neutral. But how will we get here? How will we're going to have that one? In the distribution box, there is this. There's some voltage coming here. I don't know how much is it, but here they call it transformer with center tap. They have one center tap. Basically, whatever is voltage here, there are three taps. There are three taps here. So this voltage, this is N, and this is N. You are equal. So whatever is voltage here is going to be the same here. And usually they either round this one or something. You know. Now this is your reference. You're going to have 120 and minus 120, right? Now let's look at this system. It is X, Y. You find it, right? Let's assume we have a center tap transformer here. Connected here, right? And let's call this one N, neutral. We calculate CXY. But what we need to calculate, usually we need to calculate C respect to the ground. We want to see how much is my CN, CXN, CYN. I want to calculate that. So this one was between line to line. I want to calculate the capacitance between conductor X and the neutral. Can you tell me how much is it? How much is it? It's very simple. Yes, somebody say twice, it's correct. Why? Because CXN, let's call it XN, is a VXN, sorry, Q over VXN, right? Q is Q. How much is the VXN? If, is it correct? So this is a VX1, right? This is a VX1, right? This is in the middle. This is a VXN, and this is a VY, right? Y, this way, right? VXN and VYN, they are equal, right? The only thing is they are magnitude-wise. The only thing is they have 180 degree, you know, phase difference, right? So basically, VXN is going to be VXY divided by 2. So basically, 2 times Q over VXY. Q over VXY is 2 CXY, right? It's going to be CXY. And the CXY we calculated here. How much was it? So it's going to be 2 pi epsilon. So basically, if you are going to have an electrical circuit, if this is X, this is Y, this is N, we call this one CXN, CYN, which they are equal. CXN and CYN, they are equal, right? And this is a CXY. This is an electrical circuit, the argument for this circuit. So we calculated the capacitance between two conductors with a neutral one. Something I forgot to say about the transformer, you know, just quick things I want to mention. It's not related to what we are doing now. And you may hear about it when you go somewhere. How many of you have you heard about tap changer? Tap changer. How many of you have heard about tap changer? One, two. So what is the tap changer? Can you tell me?
From what I understood, it was when they want to change the amount of windings that are on the transformer, they put it in a little section so that it's easier to do.
Exactly. See, if you look at a transformer with a tap changer, let's say this is a primary, I'm going to put it for a single phase transformer. So this is a secondary, and they give you different connection points. It's not usually like this. Let me put it this way. This is not really correct. And here, and this is your output. So basically, you can see if you are here, you connect this one here, you have this good turn, right? If you connect it to here, you are going to have a little bit more turn. If you connect it here, you have a little bit more turn. If you connect it here, you have a little more turn. What's the advantage of having this? Can somebody tell me?
Adjust your voltage.
Adjust the voltage. Ah.
By changing the number one.
Let me put it this way. Say, let's say put another tap here. I am here, right? And I have a load here. And I want to see 120 volt here and the other. I don't know. I have 1 kilowatt load, I have 120 volt, right? And here is my source. This source is fixed. Here, this side is fixed. Now, my load is going to be double or triple, whatever. What is going to happen? You are going to lose. But when the load is triple, means the current is bigger, right? When the current is bigger, means the drop voltage is bigger, right? The drop voltage is X times I, right? So basically, if this load becomes 3 times, so this voltage maybe is 110, I don't know. It's going to drop. Because here we have some delta V, right? Here we have some delta V. There is a cable, there is a transformer, those kind of things, right? So basically, this one is going to drop. When I have a lots of current, so it's going to be, for example, 110 volt, right? So if I have a tap changer, you know what I'm going to do? Oh, okay. The voltage went down. I'm going to bring this one a little bit up. Change this one connected to here, right? If I connect it to here, this voltage is going to come up, right? Or let's say other one. You said, hey, I was 1 kilowatt, suddenly my load is gone. Now I am 100 watt, right? What is going to happen? The drop voltage is going to reduce, right? Here. So suddenly you see 125 volt, 130 volt, something like that, right? So now you need to bring down the voltage. You want to keep this voltage 120 volts fixed, right? So basically, you connect this one here. Use a different taps. They call it tap changer, you know. So basically, you can put it here, 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 here. What's the disadvantage of having this thing? Two disadvantages. Cost more money. That's the first thing. Why? Because you know, if it's a regular transformer, you don't have this one. Only one head can come in here, right? That's one thing. When you are winding your transformer, you are going to have a more connection point, right? Which means more cost more money. What else? What? I'm not sure.
They don't last as long
Why?
because that switch is going around.
Yes. Why? What do you mean? Because the switch is every time you switch, there is a spark, right?
Yeah.
A spark. So basically, you need to have a switch here also. Extra cost, right? So extra cost because of the transformer structure. Extra cost because you have to have this tap changer, right? So it's more expensive. But what's the advantage? You have a regulated mode. Then you go to the power electronics one. Oh yeah, it was power electronics one. When I was teaching the thyristors, you know, I'm not sure if they do it the same or not. Look at the last year homework when you are there. They call it solid state tap changer. Solid state tap changer, it does everything automatic. It does everything automatic. It does look at this voltage. For example, you said we want 120 volt. It's going to go automatically. There is a control system. There is a control loop. It's going to change this one. But with the thyristor. Thyristors, they are like a diode, you know. They are kind of, you know, element like a diode, and they can do it. I'm not sure if professor will teach that or not, because this is more on the power side. You know, the power people, you know, they like this kind of thing. The electronic people, they less like the power side, you know. So maybe we not talk about those things. But if you want to see it, remember, when they have a power electronics one, you can check my homework from last year, you know. Tap changers. I want to type it in Google. Type it in Google. Solid state tap changer, and it will show you what they are. You know, they're pretty interesting topics. You know, to control the output code. Now we will just I want to talk about the tap changer. If you hear about the tap changer, you know what it is. You know, basically this is a variable, you know, thing you can change it to change the output voltage. We finished the single phase system. Now let's go to the three phase system. Yeah.
Do you have a problem with capacitance too when you have more wires that use that one too as well?
What the,
More capacitance?
what the, you're talking about tap changer?
Yeah.
Yeah, they have some capacitance in here. You know, there are some capacitance in here. And if it did, it's going to cause some problems. You know, there are kind of, you know, practical things when they want this transformer, they have to be very careful, you know, how to do it to not create a big, you know, capacitance. Usually for the low voltage, it's not important. But for the big one, you know, that like the 300 kV, 400 kV, for those ones, it's very important. You know, because you can see the CXY is Q over V, right? If the V is huge, you know, you see how much shaking you're going to see. How many of you have looked at the electrical panel you have at home? Guys should be, just make sure not, but the guys really goes there, right? We have an oven at home, you know, if something is wrong with this electronics thing, it start to beep every 5-6 days. I have to go shut it down from the panel and turn it on again. It's going to be good for 5 days and you have to do it again. Have you guys looked at the electrical panel? Look at the oven, you know, look at the visual they put there. Look at the oven, see the double breaker, you know. The rest is a single breaker, the oven is a double breaker, because double breaker they put it here. It's like this. You know, they are gonna, when they are breaking, they are gonna break both, you know. Break I mean disconnect, you know, the power system. Breaking means, you know, disconnect the system. When they want to disconnect, they want to disconnect both. Because if one is connected here, let's say there is only one. Right? Somebody comes to repair your oven, right? And somehow there is a ground. You put the hands here and here, boom, it's going to be short, right? Because this one is hot. If you touch only this one, there is no problem. You know, there is no current pass. But as soon as you touch this one and this one, there is a problem, right? And that's when you get to the double breaker. You know, when you open it up, they are both disconnected. Those we both disconnected. Now you put your hand anywhere and here, there's no problem because there's no current path.
Wouldn't that be true for any connection? Like, wouldn't you need a double breaker for anything then?
No. For this one, see here. For example, let's say you have a refrigerator, right? This is another refrigerator. You put the breaker here on the hot one.
Oh, yeah.
So now put your hand here and here.
Yeah.
There's no problem. You're going to 0, 0, right? But if the hot line is there, it's a problem. You know, you have to make sure you know the hot line is disconnected. So we calculated the capacitance for a single phase system. Now we are going to go for a 3-phase system. So we have a 3-wire QA QB and QC, and they are all, the distance is D, just keep it the same. Let's call this one DAC, DAB for now, and DBC. And the radius of each one is R. We have 3 conductors. They are distance DAB, DBC, DCA, and we're going to say they are all equal distance, you know, for now. Because if they are not equal, it's going to be different, you know. For now, DAB, DBC, DCA, DAB, DBC, DCA, they are all equal. And let's say DAA, DBB, DCC, they are all R, right? The radius of this. I'm going to write the equation for everything, but after that I'm going to just replace this one with this value. Now, how much is the DAB? AB, I consider A positive, right? B negative. Just keep in mind. A is positive, B is negative, right? So it's going to be the equation I raised in here. I think it was, what was the equation? It was 1 over 2 pi epsilon. Now, sigma. So I want to calculate the voltage difference between A and B because of conductor A, 1, because of conductor B, 2, and because of conductor C, 3, right? I should write 3 terms, right? So it's going to be Ln of, the first one, QA. It's going to be QA, Ln of, tell me what? I'm calculating the voltage difference between A and B because of conductor QA, charge QA. It's going to be Ln of what? And A is the positive. I'm writing it AB. Keep in mind. I'm writing it AB. It was the negative. How much is it? DAB, right? Divided by the positive is DAA, right? So it's going to be DAB over DA plus. And one more thing we have here. QA plus QB plus QC is equal to 0. That's three-phase system, right? Now I'm going to write the QB. Ln. So I want to calculate the voltage difference between A and B because of QB. It's going to be what? And A is the positive. It's going to be a negative, right? What's the negative? EDB over how much? E. So plus, now this next one. QC is going to be QC Ln of how much? So we're going to calculate the voltage difference between these two. A is positive, B is negative because of this one. It's going to be dVc over dAc, right? I don't know, this guy wants to continue all the way after that. So let's simplify it. So we said dVc and dA, we said all this one, right? Very good. How much is this? Let's get rid of this one first. How much is this? 1. How much is the ln of 1? 0. So this term is gone, right? Basically, you can understand it also simply also. You say, hey, I have a charge here is in the same distance from these two, right? Whatever voltage is creating here is going to create here also, right? Because the distance is the same, right? So basically, they cancel each other, so there is no voltage. So VAB is going to be 1 over 2 pi epsilon QA ln of D over R, right? Plus QB ln of R over B, right? Let's calculate the DAC also. DAC is going to be 2 over pi epsilon, I believe. It's going to be QA ln of D over R plus QC ln of R over DS. If you calculate the DAC, it's going to be the same. The same way. So our intention is we want to calculate the CAN, CBN, and CCN. That's what we want to calculate. So basically, to calculate the CAN, what do I need to calculate? VAN, right? If I want to calculate the capacitance of phase A respect to the ground, I need to know how much is the voltage of phase A respect to the ground divided by QA divided by that, right? So let's calculate the VA. I'm going to write this VAB plus VAC, right? So what is the VAB? Is the VAN minus VBN, right? Plus VAC is the VAN minus VCN, right? So that's what? Question? Okay. So it's going to be 2 VAN minus VBN plus VCN. How much is this? VBN plus VCN. VAN plus VBN plus VCN is equal to 0, right? That's a three-phase, balanced three-phase system, right? VAN plus VBN plus VCN is equal to 0, right? Let me write it. VAN plus VBN plus VCN is 0, right? So basically, VBN plus VCN is minus VAN, right? So this is a minus VAN. So 2 VAN minus VAN, 3 VAN, or VAN is VAB plus VAC over 3. Right? So now you know why I calculated VAB and VAC, right? I can calculate the VAN easily. VAN is going to be this one plus this one divided by 3, right? So let's calculate VAN. So VAN is going to be 1 over 3 times this one plus this one, right? So I'm going to factor in a 1 over 2 pi epsilon. It's going to be QA ln of d over r plus QB ln of r over d plus QA ln of d over r plus QC ln of r over d, right? So this one is going to be equal to 1 over 3 times 1 over 2 pi epsilon times. I have this one and this one, right? The same term. It's going to be 2 QA ln of d over r plus, I have these two terms. Both of them, they have ln of r over d, right? Let's factor in that one. It's going to be ln of r over d times what? QB plus QC, right? QB plus QC. How much is the QB plus QC? Minus QA, right? Right. If I bring this minus here, bring it to this ln. Let me write it. This one is going to be, I can write it this way, QA ln of d over r. Is this correct? Right? The QA, I put it here, minus here, right? This minus is going to be here, right? Bring it here. This one is going to be d over r, right? QA ln of d over r, and I have 2 of them here, it's going to be 3 of them, right? 3 is going to cancel this 3, so basically it's going to be 1 QA over 2 pi epsilon ln of d over r. So I calculated the VAN, right? Now I have the VAN, I can calculate the CAN. How much is the CAN? VA. Right? This is the VA. So Q is going to cancel this one, is like 2 pi epsilon over ln of V over R. How much is the CBN? This is a balanced system, right? All three are the same. And the unit I put up. The unit is farad per minute. So if you want to draw the circuit for this one, if you want to draw the circuit, this one, if this is phase A, this is phase B, C, and this is phase B, and let's say this is the neutral point, N. This is the CAN, CBN, and CCN. They're acting like this. I think I'm going to stop here now. And hopefully one more session I can finish this one. Yeah, I think I can finish it. Really happy to be here.
Can you explain again, like, the
You need to
negative?
speak loudly.
Oh, can you explain again the negative and positive? Like, I'm still confused about how you.
You know, when let's go back to the very beginning. Okay, right here. When we started, you know, we said, okay, I'm going to make it simple. I'm not going to put it like a conductor. We have a Q here, and we have a point P here, P1, and point P2 here, and this is the D1, and this is the D2. We said we want to calculate the, and we know E, what was the equation for E? Was it 2 pi x, something like that, or 2 pi x, I think. 2 pi epsilon x, I think was that. If I'm correct, it was that. You know, at any point with a distance x from this charge, the electrical field is this one, right? Now we want to calculate the difference voltage between, we want to calculate V12, which is a VP1 minus VP2. Basically, when I write it 1, 2, means 1 is positive, I'm assuming. 1 is positive, 2 is negative, right? And how did we calculate this? We went there, this is again, integral of E dx from D1 to D2, right? We calculated this way. So if you do this calculation, this one is going to be 1 over 2 pi epsilon ln of D2 over D1. Now I should just memorize this, you know, from now. We said, okay, the voltage between these two, because of this charge here, is going to be 1 over 2 pi epsilon ln of the negative distance over the ln of the negative, positive distance. Just I said to memorize it. You know, I said negative over the positive, right? This is the positive, you know, side here, and this is the negative. Any more questions? I think we are done. I was going to show some examples, but we'll leave it for kids.